In this video, we're going to discuss error estimates for finite differences. Our goal is to get a result that tells us that for vanishing mesh size, as we let the mesh size go to 0, the finite difference method converges to the true solution. That, of course, is the whole point of this finite difference method, to get an approximate solution to a differential equation. And we hope that as we let the step size be very small, the discrete solution actually converges to the true solution in some sense. That is already quite complicated. There are many different results from analysis, from calculus, and also from linear algebra that come into play here, and they all work together. So in some senses, it's going to be quite some firework of different results. For simplicity, we take a look at a very simple model problem, namely the diffusion equation, negative u prime of x equal f of x, with homogeneous Dirichlet boundary conditions. So we impose that u of a equals 0 and u of b equals 0. Throughout the discussion, we are going to encounter three terms that are quite central throughout numerical analysis, namely consistency, stability, and eventually convergence. We're going to explain each of those three terms and how they work together. Okay, again, we set up our discrete mesh. We let n be an integer at least 1, and that integer n is the number of interior nodes of our discrete mesh. And we let h equal 1 over n plus 1 be the mesh size, the step size between the different nodes. Then we let vh be r to the n plus 2, and let rh be the restriction operator, the restriction mapping, which takes a continuous function over the interval ab and produces then the vector of point values of that function over the nodal points. Okay, we've got a right-hand side f of the original diffusion equation, and then we let fh be the sampling of f along the nodal points. fh equal rhf. We just take f and take the values of f at the nodal points and puts this into a vector of size n plus 2, and that is fh. Okay, now we can set up the finite difference method. When we set up the finite difference method, we end up with a linear system of equations. Let us use the notation LH for the system matrix of the discrete boundary value problem that we construct from the finite difference method. So LH is a matrix that can be written as follows, namely 1 over h squared times the tridiagonal matrix, where we've got 2's on the main diagonal and minus 1 on the upper and lower diagonal. That's a system matrix. And then we construct the discrete solution of the finite difference method by solving a linear system of equations. That linear system of equations has the form LH times UH equal FH, where UH is the vector of unknowns and FH is the right-hand side of the linear system of equations. FH is a vector of size n, and the entries are fh1, fh2 up to fhn, just the values of fh on the interior nodes. And the solution vector UH contains the entries UH1, UH2 up to UHn, which are, of course, the entries of the discrete solution on the interior nodes. Since we are using homogeneous Dirichlet boundary conditions, we already know that UH naught and UH n plus 1 are equal 0, so we can remove them from the linear system of equations. That's just a technical simplification to ease the following discussion. As already mentioned, there are three terms that we're going to explore: consistency, stability, and convergence. And consistency is probably the easiest of those. Consistency is the most simple of those concepts, in the sense that it is a concept that is most simple to check. The question of consistency of a numerical method for a boundary value problem is as follows. If we take the values of the true solution at the nodal points, how well do we satisfy the discrete differential equation? So let us suppose that U is the true solution of the boundary value problem, and then we define a vector capital U, which is a vector of size n, by taking the values U at x1, U at x2, up to U at xn. Okay, what can we do with that vector? We already know that if I take the system matrix LH and multiply it by the discrete solution UH, then I get the right-hand side FH. But generally, if I take this vector U, where I take the samples from the original solution of the boundary value problem, and compute LH times that vector U, then I do not get the right-hand side FH. I mean, that's intuitively clear. The discrete solution satisfies the discrete boundary value problem. The true solution satisfies the true boundary value problem, but generally not the other way around. If I take the true solution and plug it into the discrete boundary value problem, it's not gonna fit right. If I take the original solution and plug it into the original boundary value problem, it's also not gonna work right. However, we can expect that even though LH times U is not the same as FH, LH times U might be reasonably close to FH. The consistency of a numerical method for a boundary value problem measures in how far LH times that vector U is close to FH. So to be precise, the consistency of the numerical method is measured by the difference LHU minus FH. That can be written in different ways. For example, we know that FH is the same as LH times UH, so we can rewrite this difference as LHU minus LHUH. And since the matrix vector product is linear, we can also rewrite this as LH times U minus UH. Those different ways of writing LHU minus FH will come in handy later. Now, for each entry of this vector LHU minus FH, we can actually use the approximation estimate for the second order difference quotient. So let us recall that FHK, the case entry of the vector of H, can be written as the right-hand side F, evaluated at the nodal point xk, and that again is the same as negative U prime prime of xk. Then again, if I take the vector LHU and take a look at the kth entry, then from the construction it should be clear that this is always the same as negative the quotient U at xk minus 1 minus 2 times U at xk plus U at xk plus 1 divided by h squared. Because the entries of the matrix LH are just taken from the formula for the second order difference quotient. And that second order difference quotient is just the same as negative U prime prime xk plus some error term. That error term has order h squared in the step size. And in fact, if we take a look back at what we have derived about the difference quotient, then more precisely we can say that the term is something that is bounded by the following, namely h squared over 3 times the maximum of the fourth derivative of u at zeta, where zeta is taken between xk minus 1 and xk plus 1. Clearly that upper bound is of order h squared, and it looks a bit pedantic at first, but we are going to use that soon. So we get the following result already. For all indices k from 1 to n, we get that LHU minus FH in the kth component is of size of order h square. And as we've seen above, that term of order h square actually can be bounded by h square and the maximum of the fourth derivative over the entire interval. At this point, let us introduce some more notation. This vector LHU minus FH is also known as the truncation error. We use the letter tau h. And tau h is equal LHU minus FH. And so each entry of the truncation error has magnitude of order h square. Okay, that's already quite a neat result. We've essentially only used the approximation estimate for the second order difference quotient. That was the central thing that we've actually used, and then we've wrapped it here in this framework of linear algebra. Okay, so we have got a component-wise estimate for the consistency. But for what I would like to do, I would also like to discuss a Euclidean norm of the truncation error. Okay, so the truncation error tau h is a vector of size n, and certainly you can just take a look at the Euclidean norm of that vector. We would like to bound this Euclidean norm from above. So take a look at the Euclidean norm of tau h. And now to get rid of the square root, I'll just square it immediately. And then we see, of course, that by definition, that is a sum where k goes from 1 up to n. And what we're summing up is LHU minus FH. Take the kth component and square it. Well, as I already discussed, we had this very pedantic error estimate involving the fourth derivative of u. And if I simply plug this in, I can see that this is upper bounded by the sum where k goes from 1 up to n of the following terms, namely h to the fourth power over 9 times the maximum of the fourth derivative of the absolute value of the fourth derivative, u prime 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 to the square over the interval xk minus 1 up to xk plus 1. Okay, one thing I can do is I factor out the cubic power of h over 9. And what I'm left with is the sum where k goes from 1 up to n of h times the maximum of the fourth derivative over the interval from k minus 1, from xk minus 1 up to xk plus 1. Now it takes the maximum of the absolute value of the fourth derivative only over these little intervals here. In fact, I can upper bound this, of course, by the maximum of the fourth derivative, its absolute value, over the entire interval from a to b. So I get the upper bound h cubed over 9 times the maximum of the absolute value of the fourth derivative to the square over the entire interval from a to b, multiplied with the sum where k goes from 1 up to n, and what I'm summing up is just this mesh size h. Of course, that last sum can be bounded very easily from above, namely I've got n times the step size h, so that is almost the length of the entire interval, b minus a. Okay, so I got an expression that involves the step size, the length of the interval, and the fourth derivative of the function u. So where did this bring us? The square of the Euclidean norm of the truncation error tau h is bound from above by h cubed over 9 times b minus a times the maximum of the absolute value of the square of the fourth derivative of u over the interval from a to b. Now I take the square root of both sides of this inequality, and that gives me, in the end, that the Euclidean norm of tau h is bound from above by h to the 3 over 2 times the square root of b minus a over 3 times the maximum of the absolute value of u prime 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 over the interval from a to b. So in particular, the truncation error tau h is of order h to the 1.5. Hooray! Next, we're going to discuss stability. In order to make this concept palpable, let us define the vector EH as U minus UH. This vector EH is in some sense the error between our sampling of the true solution and UH, which is the solution of the finite difference equations. Now, we would like to have some information about this error term. This error term somehow compares the true solution with a discrete solution. And what we know about the error term is as follows, namely, it is related to the truncation error. The truncation error tau h equals LH times U minus UH. So in particular, it is equal LH times EH. That is the relation between the truncation error and the error term EH. We already have an estimate for the truncation error, so it would be nice if we could somehow transfer this error estimate for the truncation error to get an error estimate for the error term EH. And that is the whole point of stability. Stability asks whether we can bound the error term EH in terms of the truncation error tau h. What we want in terms of concrete mathematical entities is an inequality where we have the norm of EH bounded from above by some constant CS times the norm of tau h, where CS is some non-negative constant, the stability constant, which ideally does not depend on h. As you can tell, if we have such a stability estimate, okay, tau h can be bounded in terms of the step size h. Then we have got the stability constant CS, which is independent of the step size. And so in that manner, we could immediately transfer the estimate for the truncation error to get an estimate for the error term EH, if we can prove the stability. Now, as a rule of thumb, proving consistency of a finite difference method is comparatively easy, but proving stability typically requires quite some work. So I'm going to give you an outline of a proof for a stability estimate, but we will brush over some technical details. In order to prove such a stability estimate, it is completely sufficient to prove a bound on the matrix norm of the inverse of the system matrix LH. We would like to show that the matrix norm of LH inverse is bounded from above by some constant CS, which we are going to call the stability constant. Why is that our goal? Well, we remember that since LH times EH equals tau h, if LH is invertible, then we have EH equal LH inverse times tau h. So in particular, we can use some knowledge about matrix norms, which we have seen in 170a. We have that the norm of EH equals the norm of LH inverse times tau h. And then we can use an inequality related to matrix norms. Namely, we can bound this from above by the matrix norm of LH inverse times the norm of tau h. If we can find this upper bound for the matrix norm of LH inverse, this upper bound CS, then we can use such an inequality, and then the upper norm, then the upper estimate for the norm of the truncation error gives us immediately an upper estimate for the norm of the error EH. All right, to do that, we need to show a few properties of the matrix LH. The first property we show is that LH is symmetric. In fact, it's pretty clear. We have this matrix with 2's on the main diagonal. We have entries -1 on the upper and lower diagonal. And that tridiagonal symmetric matrix is multiplied by 1 over h squared. So in particular, the resulting matrix LH must be symmetric. Okay, that's not difficult. The next step we show is that LH is positive definite, and in fact that is a bit difficult. We can check that the eigenvalues and eigenvectors of the matrix LH are given by the following formulas. we have n different eigenvalues and n eigenvectors. The eigenvalues are lambda hk, where k goes from 1 to n. And LHK is given by 4 over h squared times the sine to the square of the quotient pi k over 2 times n plus 1. A corresponding eigenvector is VHK, where k goes from 1 to n. And the entries of VHK are given as follows. The jth entry of VHK is VHK j equal 2 over n plus 1 times the sine of the quotient kj pi over n plus 1. We are not going to prove these eigenvectors and eigenvalue relations. For this, you need a few trigonometric identities. Let me just say that the trigonometric functions sine and cosine are eigenfunctions of the second derivative order operator, so to speak. And so it is kind of like can be expected that the eigenvectors of the finite differential matrix will also resemble sort of the sine functions. But that's something we're not going to go into too much detail now. Okay, what actually matters here are the eigenvalues. Namely, one can show that the eigenvalue lambda h index k is bounded from above by some positive constants, by some positive constant 1 over cs. That constant 1 over cs does not depend on the step size h. Let me say a few words about why that is true. We're not going to formally prove this, but let's take a look at the definition of the eigenvalues lambda hk. So first, we can tell that the smallest eigenvalue is going to be the eigenvalue corresponding to k equal 1, because then the argument in the sine function will be close to 0, will be closest to 0. As k goes from 1 up to n, the eigenvalues first increase, similar to the sine function, to the square of the sine function, and then they decrease again, from 0 going up and then down again. So for k equal 1, we probably get the smallest eigenvalue. And when k is equal 1, then within the sine function, we've got essentially pi over 2 times h, because h is equal 1 over n plus 1. Now, if h is small, then the square of the sine of pi over 2 times h is roughly the same as the square of pi over 2 times h. And so the term h to the square cancels out the other term, h squared in the denominator. So we can reasonably expect that, in fact, lambda hk satisfies a lower bound. Okay, with that out of the way, let's move on. We can finally prove stability. First, since LH is symmetric, it is also diagonalizable. So we can decompose LH equal x inverse times d times x, where x is an orthogonal matrix and d is a diagonal matrix with the eigenvalues of lambda h. Lambda h1, lambda h2, up to lambda hn, and that is bounded from below, as we've seen, by 1 over cs. In particular, since all the eigenvalues of LH, which are the eigenvalues of d, are bounded from below by some positive constant, the matrix D must be invertible. The inverse of LH is then given by LH inverse equal x inverse times D inverse times x. D inverse is again a diagonal matrix, and the entries are the inverse of LH1, the inverse of LH2, and so on up to the inverse of lambda hn. And those entries are bound from above by CS. we have a lower bound for the eigenvalues of D, so we get an upper bound for the eigenvalues of D inverse. And then we just recall the following fact. The matrix norm of LH inverse is the largest eigenvalue of LH inverse. And so in particular, the matrix norm of LH inverse is bounded from above by CS. And that proves stability. Okay, with consistency and stability being established, we can now discuss the convergence of the finite difference method. And by comparison, that's pretty much a piece of cake. So convergence is about how can we bound the error EH, and does it go to 0 as we decrease mesh size? Okay, we already know that LH times EH equals the truncation error tau H. And so in particular, EH equals LH inverse times the truncation error tau H. And hence we have that the norm of EH is the same as the norm of LH inverse times tau H. Now we can use an inequality about matrix norms, namely, we immediately get that the norm of EH is bounded from above by the matrix norm of LH inverse times the norm of tau H. Okay, now first from stability, we get that the norm of EH is bounded from above by the stability constant CS times the norm of tau H. And from consistency, we can use that we have a bound on the truncation error tau H, and that together gives us the norm of EH is bounded from above by the stability constant CS times H to the 3 over 2 times the square root of B minus A over 3 times the maximum of the fourth derivative over the interval from A to B. So in particular, we get the same power of H in the error estimate for the error term EH that we already have in the error estimate for the truncation error tau H. As the mesh size H goes to 0, the Euclidean norm of the error term EH goes to 0 as well. I've implemented the finite difference scheme for the Poisson problem over the interval from 0 to 1 with Dirichlet boundary conditions. And what we see here is an approximation to the Poisson problem. Negative u prime prime of x equal 4 times pi square sine of 2 pi x. The solution to that differential equation with Dirichlet boundary conditions is simply the function sine of 2 pi x. And we see a rough approximation here already on the screen. Here I've got n equal 10 interior nodes. But we can also tell that the approximation is far from perfect. So let's increase the size of nodes. Here we have got the discrete solution. Here we've got the discrete solution with double the number of points, n equal 20. And here we see an approximation with 40 interior nodes. And you can tell clearly it converges to the right solution.